Hello and welcome. A very good afternoon, and I welcome you to the third live session for the subject Kinematics of Machinery. I hope all of you are fit and fine. So here in these live sessions, we are discussing about machines, mechanisms, links, and all about all of them, the life that they live and how is it making our lives simpler. In the previous sessions, we have already discussed about what is a machine and how a machine is made up of, let's say the components of a machine, like mechanisms, various types of links. And then we have learned that when a machine is moving, what kind of velocity and the components that they are facing. Also, related to the velocity, we have talked about acceleration. Now, in today's session, let us see how, which kind of pairs they are forming and how they are functioning. Here in this session, we will be discussing about mechanisms with lower pairs, specifically with lower pairs. So in the first session, we have talked about what is a lower pair. Just to revise, let us say lower pairs are the pair of links which are having a surface contact. So let us see what they are. Let us see what session has. So this mechanisms with lower pairs actually will have straight line motion mechanisms. Now how and what kind of straight line motion mechanisms are there? Maybe, let's say if I say straight line, you may be asking me whether the straight line is an exact straight line or an approximate straight line. So here in this session, we will be discussing both the types, saying the exact straight lines and the approximate straight line. Let us go one by one. Let us discuss the exact straight line first. Having the exact straight line motion mechanisms, they are possible by using only turning pairs and also possible by using one sliding pair. So let us see how it is possible by using turning pairs only. So using turning pairs, we have specifically these two types of mechanisms. First one is the Peculiar mechanism. Second one is the Hart's mechanism. So Peculiar mechanism, we will see the function in the next slides anyway. But let us talk about this Peculiar mechanism. They are able to trace a straight line having number of links. We will see the analysis a little later. Talk about the Hart's mechanism. That is also having a number of links and it is also tracing an exact straight line. Why am I stressing on exact straight line? We will see in the next slides. So see, this is the Peculiar mechanism. This is how it functions. Can you see? There are the number of links, two green links. One is a blue link and one is a dotted line. This is nothing but the fixed link. That's why it's not moving. It is constrained and not at all moving. There is no motion in that. So this particular link is a fixed link. Other than that, we have different other links and total number of links in Peculiar mechanism are 8. Let us see the analysis, how it goes. See, in this diagram, it is just the line diagram of the same mechanism that we have seen just before. This is the mechanism of having the links, 8 links I told you. So OA is a link, OE is a link, OB, OD, then ED, EB, BC and CD. There are total 8 links in this. Point E is able to make a complete whole circle and the radial distance from O is OE. OA is a fixed link. And we have to see that how the C point is tracing a straight line when the OA line is produced. So let us have the analysis. We say that E point is constrained to move along the circumference of the circle. That is what I told you. It is completing one whole circle. We know how that is called. What is that called? So this E is constrained to complete one whole revolution about the point O only. Okay? Now here, there are few more constraints saying that length of AD is equal to AB. Also the lengths of BE, ED, DC and BC are equal. So let us say length of AD is equal to length of AB and AD is equal to AB, BC is equal to CD is equal to DE is equal to EB. Also the lengths of here length of this particular link and this particular link are equal. So here, can I mark this again? AD is equal to AB, then this equal to this, equal to this, equal to this. All the four sides are same over here, and the lengths of these two links are equal. Then what are we actually analyzing over here? I'm saying just by statement that the C point is tracing a straight line. So let us see how far it is true. Let us prove that. So our required to prove is that point C is moving in a straight line which is perpendicular to that OA when it is produced. Further, so let us say I'm talking about the rhombus BCDE, this particular rhombus. So when I talk about that particular rhombus, EC and BD are the diagonals. So we know that property of a rhombus is that the diagonals always intersect each other at 90 degrees. So that is what it is bisecting, and they are at right angles. So we can say that ELB and CLB are 90 degrees. See, I have given this mark also. This mark says they are 90 degrees to each other. They are right angles to each other. So when AEF will be at right angles, if this is at right angles, and for all positions, as it is angle subtended by the diameter on the circumference, it is also making a 90 degrees. This is the property of a circle. When we learn about the geometry in mathematics, when we talk about circle, the topic of circle says that whenever the diameter is, let's say, making any angle at the center, those 2 points, whenever they are subtending an angle anywhere, that is the half of this angle that is made at the center. So since this is 180, this is going to be 90. Okay? So angle AEF is going to be 90 there. So let us first prove that this particular line is a straight line. Then we can go for the proving of point C whenever it is tracing a straight line, whenever it is AO produced at G. So we are talking about the triangle AEB and AED. This particular triangle and this particular triangle. I'm talking about those two triangles. Let us prove the similarity in between them. In the diagram you can see that in these two triangles AE is common, and since I told you that AB is equal to AB, AB is equal to AD. So this is one of the property. So I can write down that AE from this triangle AEB and ADE, AB is equal to AD, again given. BE is equal to ED, that is also given, and AE is common. So I can say that AEB and ADE are similar triangles. Since they are similar triangles, I can also say that angle EAB and angle EAD are equal to each other. So when I say EAB and EAD are equal to each other, that means that AE line, see this AE line is there, that is bisecting this particular triangle. Let us draw freshly. So I'm talking about this particular angle is, this particular angle is equal to this particular angle. When these two angles are said to be equal, then I can say that this particular line is bisecting this total angle. Yes? So when it is bisecting, then let us say this angle is equal to this angle. That is what is proved over here. So E lies on the bisector of the triangle DAB. Okay? Now again consider this particular triangle of ACB and ACD. Let us see what they are. ACD, this bigger triangle now, and this bigger triangle. ACB and ACD. ACD. In this also, again, AD is equal to AB, BC is equal to CD, and AC is equal to AC, again common. So by these three conditions, again those two triangles are similar. When they are again similar, they are again bisecting. CAB and CAD are going to be equal. So when they are equal, they are again the bisectors of the triangle DAB. Hence I can say that AEC is a straight line. See, I mean to say that from the bigger triangle also, this particular angle is made to be equal to this particular angle. Again, this point C is lying on the bisector of this bigger angle. So hence, I can say that E and C, they are lying on the same line and they are a straight line. That is what is proved over here. AEC is a straight line. Now, if I consider right angle triangle ALB, this is nothing but ALB. Let us go fresh again. So, I am talking about ALB, this particular triangle. See, ALB. So, AB is said to be the hypotenuse. This is nothing but the adjacent side. This is the opposite side. So, by using the Pythagoras theorem, I can write that AB square is equal to AL square plus BL square. That is what we have written. AB square is equal to AL square plus LB square. Similarly, when I take right angle triangle of CLB, see CLB, this particular smaller triangle, I can say that BC square is equal to BL square plus LC square. Same thing is written over here. BC square is equal to CL square plus LB square. Now I will subtract these two, 3 minus 4. This equation AB square minus BC square. So AB square minus, this is equation number 3 minus 4. I am sorry, there was a small error. So AB square minus BC square, where AB is also written as AL square minus CL square, and see AL square minus LB square minus CL square minus LB square. So when I see AL square minus CL square plus LB square minus LB square, these two gets cancelled. So when these two are cancelled, it is forming a formula of A square minus B square. So A plus B into A minus B. Then again you can write here AL plus CL is nothing but AC. See, AL plus CL. This is total of AC. Then AL minus CL, I am writing about AL minus CL. So this CL is equal to EL. So can I write AL minus EL? Again it will form the line of AE. So finally it is AL minus CL is converted into AL minus EL and then finally AE. So let us see how it is. AC into AE. AC into AE. But length of AB and length of BC are fixed lengths. So when these two are fixed, they are constant. So can I say the product of these two also is some constant? Some constant. So if AB and BC are constant, then this product is also constant. If these two are remaining constant, then of course C is tracing a straight line which is perpendicular to the AO when produced till G. That is what was required to prove. So hence point C traces a straight path perpendicular to the diameter AO whenever it is produced. This is all about Pascalian mechanism. Now next comes Hart mechanism. You must be wondering why there are two mechanisms giving the same purpose. There is a small twist. This mechanism is having 8 links. They have let's say optimized and given a lesser number of links following for giving the same purpose. So Hart's mechanism is having 6 links. This is having 6 links and you can count over here. There are 6 links and this is also giving an exact straight line. This is the function of a Hart's mechanism. This is how it works. Once we follow this, then we can go for the analysis of the same. So this is this point whenever it is taken on this particular link. See how many links are there? 1, 2, if it's not visible. This is first link, second link, then this is third link, fourth link, fifth link and sixth link. So there are total of 6 links. We can see it in line diagram again. See here, this is a line diagram of the same Hart's mechanism. This is particular link OE is a fixed link. Then we have a link of BD, then LM, BM and DL. So there are total of 6 links, 1, 2, 3, 4, 5 and 6. 6 links are there, in which again E is constrained to complete one whole revolution. E is completing one whole circle here. And here also we will try to prove this point C is tracing a straight line whenever AO is produced for this mechanism. The same concept is seen over here. So you have different triangles. Here we will consider, this is a trapezium. You can see BDML is forming a trapezium. BDML is forming a trapezium here. You can see that. Right? So here we will consider, let us say we will have a point C which is located on DL link, and whenever we are trying to prove the tracing of that particular point, we will have to prove that that is producing an exact straight line whenever the diameter is produced, diameter AO is produced. A similar case as the previous link, previous mechanism called Pastellier mechanism. Here the only benefit is, here they are having only 6 mechanisms. So let us see how we can prove that point C is producing a straight line. Here we will consider this particular triangle. Let us say BDM and BAE. You can see this particular triangle, this particular triangle. If you see these two triangles, they are similar triangles. So once they are similar triangles, can I write the ratios like this? AB by BD is equal to BE by BM. Can I write that? AB by BD is equal to BE by BM. That is what I have written over here. So we got this condition. Whenever we are trying to take the other triangle, let us say see this triangle now. The one with the yellow line. This is the triangle. Here also you can see that they are considered to be a similar triangle. So based on the ratios, I have written all the 3 possible ratios, saying AB by BD is equal to BE by BM is equal to CL by LD. So here, by this I can say that it can be proved that OE is rotating about a circle. It is making a whole circle about point O. And point C is perpendicular to this point, let's say line that is producing diameter over here till point G. So let us see how we can prove that. First of all, we have to prove that AEC is actually a straight line. So let us see how can we do that. We have to first consider BDM triangle. See, same ratio I have taken over here. In this triangle, we can say like this, AB by BD is equal to BE by BM. If I say that, then we are saying that the line that is AE is parallel to DM. By this I can say that this line is parallel to this particular line. AE is parallel to DM. But it is already given that DM and BL are parallel to each other. It is already given that DM is parallel to BL. And by the proof I am saying that AE is parallel to DM. AE is parallel to DM. So by this condition and this condition, can I say that AE is parallel to BL? Yes, that is what I have proved. Hence, AE is parallel to BL. Now, the next triangle that we will take, I told you DBL, the bigger triangle, the yellow triangle we will take here. And from that, if I want to write the ratios, I will write like AB by BD is equal to CL by LD. Then the similar cases will be followed, and we can say that AC is parallel to BL and then parallel to DM. So now AE and AC both are parallel to BL and DM, right? So when it is parallel, I can say that AE and AC. So by theory, I can say that E and point C, they are lying on the same straight line. So AC is proved to be a straight line first. Now let us find what is the product of AE into AC. Why we are finding the product of AE into AC? Because in the previous case we have seen that if we prove that AE into AC is proved to be a constant, then I can say that that point C is tracing a exact straight line whenever the diameter of that particular circle is produced. Yes? So let us now first our aim is to find out the product of AE into AC. So let us see how that can be proved. Now I will consider the triangle ABE and DBM. Since AE is parallel to DM, we can write this AE by DM is equal to AB by BD. So AE will be given as AB by BD into DM, just the cross multiplication there. So let us consider that to be first equation. Also in the second triangle, the consideration of second triangle DAC and DBL, we will write this equation, this ratio AC by BL is equal to AD by BD. Again AC is equal to AD by BD into BL. That's considered to be the second equation. Now if I multiply AE into AC, if I multiply the whole right hand side, that from the previous equation, from first equation and second equation, we get this equation AB into AD by BD square into DM into BL. Now we know that this particular term is totally constant. Why? Because I told you there are total 6 links in this mechanism which are having some constant lengths, which are not altered. So this particular term totally becomes constant. Now there are two different terms that we do not know about. They are all foreign terms here. So we are talking about DM and BL, and we have to find out what are the exact lengths of DM and BL, whether they are constant or not, in order to find out whether this AE and AC can be proved to be constant or not. So let us now, our main aim is to find the product of DM and BL. For this, there is a small construction for this. So from L, I will drop down a perpendicular at N, and which is parallel to BD, parallel line. So here I will name it as N, and here I will name it as P. So DM I can write as DN plus NM, DN plus NM, and BL can be written as DP. So DP again can be written as DN minus PN and DN minus PN. See, DP is written as DN minus PN. So DN minus PN left over with DP. So NP is also equal to NM. So I have written DN minus PN is equal to DN minus NM. So if I substitute here, I will get DM into BL is equal to DN plus NM, DN minus NM. So A plus B, A minus B formula. So I can write A square minus B square. So which is DN square minus Ln square minus Lm square minus Ln square. So if I write that way, if I expand this formula, if I expand these terms, I finally get it to be DL square minus Lm square. Now DL and Lm are already known links. They are already present in that. I told you 6 links are there in this, which are having some constant lengths and not altered. So they are already constant. So if I say that DM and BL are produced to be constant, if I put this constant term over here and I find it that AE into AC is constant into constant, finally they get it to be again another constant. So let us now see, in this equation AE and AC are found to be constant. Let us keep it as fourth equation. Now what is exactly AE from this particular line diagram? AE is again splitted into trigonometric terms, say AS plus SE. AS plus SE. So AS is again taken as, see, AS plus SE. Here also is a small construction. From the point, center point, you have to drop down a perpendicular over here, which is making theta angle here and theta angle here and perpendicular over here. So I can write AE is nothing but the summation of AS plus SE, and individually they are having some trigonometric ratios, and AS can be written as AO cos theta and SE can be written as OE cos theta. OE and AO are having same length, so I can convert OE into again AO. So here it is AO cos theta plus AO cos theta, which is giving you 2AO cos theta. Now in the triangle AGC, you can take this particular triangle AGC. We can see that AC is equal to AG by cos theta. AG is equal to actually AC cos theta. So AC I have taken AG by cos theta. See, if I multiply this AE and AC, see AE into AC will give you 2AO cos theta into AG by cos theta. So this is cos theta and cos theta gets cancelled. It is 2AO into AG. So 2AO and AG is equal to, we know that AE into AC is constant, earlierly already proved. So I can write 2A into AG is equal to some constant. But length AO is already fixed because we have seen in the diagram, see AO length is already fixed here. So AO is already fixed. If this particular term is fixed, definitely AG is going to be constant. So hence, this means that point C is always tracing a straight line, and whenever it is let's say intersecting at the point whenever the diameter is produced at point G. So it is always the same point G at the distance AG from point A. Thus the trace of point C is a straight line. That is what was required to prove. This is about the Hart's mechanism. So two mechanisms with turning pairs is clear. I also told that exact straight line mechanism is also possible using one sliding pair. So what is that? Let us see. So using one sliding pair, the mechanism is called as Scott-Russell mechanism. Let us see how that looks. See, here there are only 3 links, 1, 2 and 3. The third one is the element, that is the slider element. So see, 1 link, 2 link and the third element, the slider. It is having one sliding pair. So let us analyze this one. See, this is the sliding pair, this is 1 link, this is 1 link and this is the third element, slider. So this is how it is looking like. Here also I have to prove that this point B is tracing a straight line and subtending a 90 degrees angle over here. So let us see how can we prove that. So here we have AC is equal to AB is equal to OA, that is a given condition. Slider C is constrained to move only horizontally. Of course, we have seen in slider crank mechanism also how the slider is horizontally constrained. Horizontal motion is constrained for that. So here also we are considering that the slider's element C is having a constrained motion and it is only moving horizontally. So what is required to prove? It is required to prove that B is moving in a straight line perpendicular to the OC line. B is tracing a straight line which is perpendicular to this OC line. So what we have to do is take O as a center and BC as the diameter, draw another circle which is passing through point B and point C, also point O. Okay. So when we see this triangle, can we see this triangle again? Here also BC is the diameter and the angle made over here is 180 again. 180. See the line over here is the diameter and the angle made over here is 180. 180 degrees. So in the previous case also I told you whenever the angle made at the center, it is always the half of the angle which is subtended at the circumference. So if it is 180, half of 180 is 90, so the angle over here is 90. It is making a right angle. So we have half the work we have done. That OB line is subtending a right angle on this OC. That's clear. Now C is tracing a horizontal line. So it is already given in the question that OC is always going to be horizontal. So 90 degrees to a horizontal line is always going to be a vertical straight line. So by those conditions, I can say that if OC is constrained to be a horizontal line and OB is perpendicular to OC, definitely BO is a straight vertical line. So those conditions are written over here, and finally we say that hence COB will always be a right angle, that's what we have said, and therefore a line joining O to B will always be a straight line perpendicular to OC. Thus the locus of point B will be always straight line perpendicular to OC. This is what was required to prove, and it was very simple using a circle and the topic that we are already covering in previous mathematics subject. Those properties if we apply over here, it is very simple to prove. Let us see the next next part of the total session which says approximate straight lines. Till now we have been talking about exact straight lines, but the straight lines are also existing in approximately. So what is this approximate straight line? We will see in the next slides. So let's talk about approximate straight line. Whenever you hear the word approximate, that means it is not only point to point straight. So if I draw a line like this, and I say, is it an exact straight line? You will say it is not at all a straight line. But I will say that it is a straight line, but approximate straight line. How it is possible? If I consider the part from here to here, it is definitely a straight line. But if I consider the whole part from here to here, it is definitely comprising of certain curves. So of course it is not a straight line. So it is a combination actually. It is depending on how much part we are considering. So I will say that this is a straight line, but approximate straight line. So how many such kind of mechanisms are actually existing? Let us see. There are totally 4 types of mechanisms. The first one being Watt's mechanism. The second one is the grasshopper mechanism, Chebyshev's mechanism, Roberts mechanism. So let us learn about each of them individually. See, this is how a Watt's mechanism functions. See, so this is nothing but this particular curve is nothing but the tracing point of this particular round. Can you see? This is a tracing point. This particular point is tracing the path of this mechanism. If you can see, it is making a loop over here and a loop over here. But if I consider the part from here to here, it is a straight line. Can you see that? When you consider the point to be at the mean position, see here it is the mean position. So mean position, whenever this link or mechanism is forming, this link and the red and the green links are parallel to each other. That is a mean position for this mechanism. See, this OD link and BC link are parallel to each other, and this is particularly your mean point. So whenever you are tracing, the link is oscillating like this and like this over here and here. See, A point reaches to A dash and then A double dash. B reaches to B dash and B double dash. So that is nothing but the path of that particular link, OA and BC. Okay. So at the mean position, always observe that the 2 links BC and OA are parallel to each other. Let us go to the next mechanism, saying grasshopper mechanism. So what is a grasshopper mechanism? See, it looks like a grasshopper, of course. That is how it has got its name. You can also ask me that it is a straight line. No, of course not. Whenever it is crossing this point, it is going to trace a curve like this. So that's why it is called as the approximate straight line. See, this is how it is proving. The OC link is moving, oscillating. It is taking the point C1 and then C2. Whenever this link OA is displaced from OA1 to OA2, and whenever it is extending over here, after this it is going to turn like this and forming an approximate straight line here. Next comes Chebyshev's mechanism. See, that is the tracing path. So approximate straight line. From here to here it is forming a straight line, and rest of the path is tracing a curve. So let us see how the analysis of this particular mechanism goes. See, this is how the motion and the line diagram are correlated. So this is a link, let's say OA is there, OC and AD are there. So let us consider that CD link being 1 unit and the length from OA is y and OC is some x. Let us see how the link ratios go forward. So let us say CD is equal to 1 unit and OA is y units and OC is x units. So we have to actually find what? Let's say CD is to OA is to OC. That is what we have to finally find. So let us see how we can prove it. So once the motion of this particular mechanism is moving this side and this side, the CD link is turning like this and it is getting, D is reaching point D1 and C is reaching point C2. C1, sorry. The point C is going and tracing this path and reaching the point C1. D is reaching D1 and this point, particular B point, is nothing but taken as a midpoint of that particular link. CD is again tracing a point over here, that is B1. Okay. So if I consider this triangle OD1A, OD1A, from that triangle, if I want to formulate from Pythagoras theorem, I can say that AD1 square is equal to OD1 square plus OA square. Can I write that? So AD1 square is, let us take it to be, AD1 is AD. Is it true? Because see, whenever the mechanism is moving, the link lengths won't change. Whenever they are moving this side or this side, the link lengths will not change. So D point is just tracing and forming and reaching the point D1. That's it. They are not getting elongated or shortened. So the length of AD will be same as the length of AD1. So can I say that is x? So can I write x square is equal to OD1. Now OD1 can be written as OC1 minus C1 D1. Plus OA square is again y square. Now OC1 is again OC. Is it true? So OC1 is OC, 1 is again OC, then C1 D1 is nothing but CD. So x square is equal to OC is again x square minus CD is 1 plus y square. So if I apply the formula for A minus B whole square, I can write x square plus 1 plus, sorry, minus let us write this term again. It is x square is equal to x square plus 1 minus 2x plus y square. So x square and x square gets cancelled here. So 1 is equal to 1 minus 2x plus y square. So again 1 and 1 also gets cancelled. So I can write 2x is equal to y square. Hence x is equal to y square by 2. So we have got x is equal to y square by 2. Then from the triangle, next time I will take the triangle OCE. Now from the triangle OCE, we will take that from triangle OCE. If I consider again the Pythagoras theorem, OC square is equal to CE square plus OE square. See, the Pythagoras theorem says that the hypotenuse square is equal to the adjacent side square plus the opposite side square. So OC square is equal to OE square plus CE square. That's what we have written. OC square is again nothing but x square is equal to CE square. Now what is this CE? CE is B1O. Okay. So B1O plus OE square. OE is nothing but OA minus AE. Now OA minus AE is nothing but OA minus CB2. OA minus CB2. Okay. So when you follow all these equations, let us say B1O. So B1O is nothing but OC1 minus C1B1. OC is nothing but again OC1 is OC, C1B1 is CB. Similarly here also OA is nothing but Y minus CB2 is nothing but BB2 minus BC. BB2 minus BC. So Y minus BB2 is what? BB2 is totally, this is one link, this is one link. So BB2 is nothing but half, this is Y. This total B1, B2 is Y. So B1, B2, we are writing CB2 as half of 1 by 2. Can I write this total CB2 as 1 by 2 directly? So here OC is nothing but again X, BC is half, so when you expand this totally, you will get again X value like some Y. Let us solve it. X square plus 1 by 4 minus 2 into X into 1 by 2 plus Y square plus 1 by 4 minus 2 into Y into 1 by 2. So finally you will get some value for X. And here you have got X is equal to Y square by 2. So when you substitute this one and this one, you will finally get the equation as CD is to OA is to OC is equal to 1 is to 2 is to 2.5. You can further solve it and please let me know if you have got the same equation, same ratio. Next comes Roberts mechanism. So Roberts mechanism looks like this, something like this. And here also you can see it is tracing a straight line from here to here. But whenever it is going a little away, it is starting to make a curve over here and here. It is starting to make a curve over here. So of course, it is tracing a approximate straight line again. So let us see the line diagram for this. There are links over here, OC and AD, and B is considered to be the midpoint, which is the tracing point. From there, I am, let's say, attaching a link over here, which is going to trace us the path. So whenever the path is traced, you can see that it is going beyond this and forming a curve, but till here, it is making a straight line. So I can say that from this point to this point, it is a straight line, but whenever it is following the beyond, it is going beyond this one, it is tracing a curve or a totally on the whole, I can say that it is making a approximate straight line. This is one more example of a pantograph. Pantograph function is to, let's say, trace or give a larger or a smaller diagrams which is already existing. This is how it is also, this is also tracing approximate straight line. You can see the loop that it is making, and I'll show you how it is from where to where. See, from here to here, if you can see, it is tracing a straight line. Remaining part, it is all totally making a loop and a curve. So it is also giving one of the example for approximate straight line. It is also used in functions like this whenever you are having a piston and a pressure is exerted. So till here we have been talking about the mechanisms with lower pairs which are having exact and approximate straight lines. The next part of this video says that we are going to learn about the steering gears. How are the steering, let's say, what is the major function, what is the major factor which is deciding how and where and how, which way are the steerings to be, let's say, designed. So let us say we will learn about the steering gears, what are the correct condition, how are they arranged, and what factors they depend on. So see, the steering means you are, whenever you are driving a vehicle, the total directions that you are giving to a vehicle depends on how you are handling the steering. So see, there are the front wheels, the back wheels are there. You already know that the front wheels are the one which are controlling the directions and the back wheels are just the followers. So see that these are the front wheels. Whenever you see the distance between the front wheel and the back wheel, that is taken as L over here. So here this is the distance, this is the W over here. And the wheel track is taken from the center of this wheel to this wheel, that is taken as the wheel track A. So all the conventions are given over here. A is nothing but the wheel track, W is the distance between the pivots for the front axle to this axle. Front two axles A and B, the distance between those 2 points taken as a W. L is taken to be the wheelbase, and here you can see these two angles theta and phi. These are the angles made by the stub axles. Let's say when they are turning left or right, they are making certain turns. Whenever they are making turns, they are making certain angular displacements. So those angular displacements are represented using theta and phi here. So theta here is the angle made by the inner wheels, and phi is the angle made by the outer wheels. Here these 2 points are very, very important, because in the next slide I will be discussing how the theta and the phi, they are related to each other. So let us say if I take the triangles, let us say EIA, this particular triangle, and if I want to write cot theta, how will I write cot theta? See, tan theta is adjacent by opposite. So if I write cot theta is 1 by tan theta, so I will write EI by AO. Okay? So EI by AO. Same thing if I consider this triangle, this particular triangle, let's say E, B and I. What is this I basically? Because these points are already covered in the second unit, which is velocity and acceleration. This I represents the instantaneous center. So instantaneous center is with this collinear to this particular line which is extending from the back wheels here, you can see. Okay, so okay, let us come back, cot phi. So for cot phi I have to consider this bigger triangle, which is EI by EB. EB. So EB can be written as again EA by AB. Let's say if I write this one as EI by EB is written as EA plus AB. So finally, when you let's say subtract these two, you will get the equation as cot phi minus cot theta is equal to W by L. Try to solve this. Again, cot phi is nothing but this way and cot theta is this way. EI is nothing but the same length as L, and AO is nothing but, it will get cancelled actually. So AB is nothing but your distance, that is W. So it will come in the terms of W by L here. If you substitute and see, you will see it. So this condition is considered to be the correct condition for the steering. So here you can see that the angle made by the inner wheels is always greater than the angle turned by the outer wheel here. So I will say that theta is always greater than phi. theta is always greater than phi here. Okay. So when learning about the different types of steering gears, we basically majorly have two different types of steering gears. One is the Davis steering gear, the other one is the Ackermann's steering gear. Let us learn about one of them in the, let's say two of them individually. First of all, Davis steering gear, it looks like this somehow, looks like this. We have only taken the front part of the total chassis. So here these are the front wheels, let's say the innermost wheel, this is the outermost wheel. So only the front part we have taken. Now this total arrangement that is there, it is given by the Davis steering gear mechanism. There is a slider S1 here and S2 here, there are two sliders here, and PAG is considered to be the bell crank lever this side, and QBF is the bell crank lever the right side. And the distance between these two sliders are given as, these two links are given as H. So this is how the basics Davis steering gear mechanism looks like before taking any turn. Once it is taking a turn, let us say it is taking a left turn. So once it is taking a left turn, your L is pushed towards L dash, making an angle theta since it is turning angle theta here, and your M turns to M dash, again it is making an angle phi here, so it is turning this side. So now here let us find out what is the correct condition for the steering gear for the Davis. So let us consider this particular, what is it is turning? It is turning about this particular angle. So how much it is again? Tan of, I will write alpha minus theta. Tan alpha minus theta is equal to, tan means the adjacent, the opposite by adjacent. So it is, let us say, d minus x by h. So it is d minus x by h. Tan A minus B. Tan A minus B, what is it? Tan A minus B is the formula for, let us say the formula for that is tan A plus tan B by 1 minus, or is it, let us say, tan alpha into tan phi. Okay. So what is tan theta? Previous case you have seen tan alpha. Tan alpha is nothing but, this is tan alpha, this is the triangle, right? So if you are taking tan alpha, it is opposite by adjacent. Opposite by adjacent is taken as d by h. This is nothing but h. This is d. So d by h. So tan alpha I will take it as d by h. So if I substitute in this equation, you will get, let us say, d by h minus tan theta by 1 plus tan alpha is d by h into tan theta. Okay, which is equal to d minus x by h. So if you take this, let us say tan theta is equal to, you will get an equation. Similarly, if you take for the right hand side, you will get, see this total angle becomes alpha plus phi now. So you will get tan alpha plus phi. Why here phi? Because this outer wheels are making angle phi instead of making theta. They are not the equal angles. So here we will get, earlier it was d distance and now they have formed d plus x. So you will get d plus x by h. So same thing here also, you will let's say tan alpha plus tan phi by 1 minus tan alpha into tan phi d plus x by h, and if you substitute tan alpha is equal to d by h again, you will get tan phi is equal to 1 equation. But our condition we know. Okay, so coming back to tan theta and tan phi, you get, let's say tan theta is, if I want to convert this into cot phi, cot theta, I will get 1 by tan theta. Similarly, if I want to write cot phi, I will get 1 by tan phi. So when you convert that tan theta into 1 by tan theta and cot phi into 1 by tan phi, and you know already that the correct steering gear mechanism condition is cot phi minus cot theta is W by L. When you calculate that for Davis mechanism, you get the equation as this one. Tan alpha is equal to W by 2L. So this is the equation. Once you solve and get for tan alpha, because alpha is nothing but the angle that it is turning, right? So alpha is the angle made by this particular perpendicular to the angle over here, bell crank lever angle I told you. See previous slide if you see this is nothing but the alpha. At what angle these stub axles are supposed to be made or put over there so that it follows the steering gear, correct steering gear mechanism condition, that is what is required to find. So this alpha is actually design factor here. So if I want to know what is how much alpha, what is the correct condition for steering gear for Davis, I need to find what is the approximately what is the value for alpha. So that is how we have calculated and found that the tan alpha is equal to W by 2L here. What is W here? See this is W for the first one I told you, this is nothing but the wheel base, W. What is L here? L is nothing but, sorry, W is the distance between the two pivots. Sorry, W is the distance between this pivot to this pivot. Pivot is nothing but the joining condition of this link and this link. So this is the pivot and this is the pivot. The distance between these two is taken as W. So this pivot and this pivot distance is taken as W here. And the distance between the front wheel to the back wheel we are taking as the wheel base is taken as the L here. So that's how we have taken it. So finally we get the condition for tan alpha is equal to W by 2L. Next comes Ackerman's steering gear. So why are we actually going for this second type of steering gear? We already have one type. So why do you think we are going for the other one? There was some loophole while following this Davis mechanism, Davis steering gear. See, I told you there is a slider over here and slider over here. So whenever you have sliders, you must be understanding that slider makes a larger surface area contact. So larger surface area contact and it is sliding multiple number of times, it is making that particular link to wear and tear on a higher level. So how can we reduce that? Instead of a sliding mechanism, if I put a turning pair, instead of a sliding pair, I am replacing that sliders with a turning pair of links. So if I turn and change that, so that is how it is changed. See here there is no slider. Slider is let's say eradicated over there, that is taken off. And there is a turning link over here. And for steering gear for Davis, you had the total arrangement ahead of the front wheel, in front of the front wheel. But what they told was, it is better that we have this arrangement at the back of the front wheel. So at the back of the front wheel, this is the arrangement. See, there is a stub axle over same arrangement, but instead of sliding pairs, we have a turning pair here. And instead of this arrangement being in front of the front wheel, we are making this total arrangement at the back of the front wheel. See, here also we can prove that it is having the same, let's say, here, this is the projection over here. Let's say let's say R, S, and the projection of particular M point and M dash is, let's say, some X and Y. Okay. So how much angle is it producing? Let us say again inner wheels is taking a left turn and making an angle of theta. The same angle at the outer wheel is made at the angle of phi. So here you can say that this particular link AL actually at the position of AL is moving towards right side, and M is moving towards further right side, that is reaching the point M dash. So I can say that the link lengths are not again changing, not changing at all. The length of the links cannot change. They are just changing the position. They are changing the tracing point. So instead of L, it is reaching L dash. Instead of M, it is reaching the M dash position. So if I see the projection over here from L to L dash, the distance over here horizontally is RS. Same thing, it is XY here. I am talking about XY small letters here and here RS capital letters. So if a link from the left side, if it is moving and giving the same kind of constrained motion to the right side, the projection should be, the distance moved horizontally should be equal. That is the main agenda here. So I will say that the projection of RS, projection of L dash is equal to projection of M dash. Only then I can justify this particular movement. So this I am saying for instance I am taking this projection of L dash as this one, this particular distance if I want to find. It is RS. It is equal to, here it is, let us say XY. So if I prove RS is equal to XY, I will definitely get some condition. So let us say if RS, how can I say that RS, what is let us say SAS value? So RS is nothing but AS minus AR. Similarly, XY is taken as, let us say this distance XB plus BY. So how can I say AS? AS is nothing but, see this is particular triangle. Let us, so this AS is this particular triangle. AS if I want to find. Now for this I require this angle. That angle can be obtained when you know that this particular stub axle is here like this particular link and this particular link is at right angles to each other. So can you see that this is making alpha, this is theta. So what will be this one? This one will be 90 minus alpha plus theta. So I want SAS. So AS is going to be the adjacent part. So AS follows the cos condition. Cos of 90 minus alpha plus theta. Minus AR is this condition. So this AR. So AR is following this particular triangle. AR is following that particular triangle. So if it is 90 minus alpha, if I do, if it is 90 minus alpha, it will follow the same condition. So I will say again AR is nothing but cos of 90 minus alpha. Similarly for XB also, XB is nothing but this particular triangle. XB is this particular triangle. So here it is, I will say this particular angle here, phi plus this is alpha. This is alpha minus phi here, and if I take this particular angle, this is again phi minus alpha. Okay. So if I follow the same condition there, you will finally get tan alpha is equal to sin phi minus sin theta by cos theta plus cos phi minus 2. You solve the same condition and then you have to just expand here. Cos 90 minus theta is nothing but sin theta. Theta, in place of theta you have alpha plus theta. So for this term you will have sin of alpha plus theta. Same thing, cos 90 minus alpha is cos sin alpha is equal to this xb plus by in terms of cos and sin. So finally when you convert that, you will get tan alpha is equal to sin phi minus sin theta by cos theta plus cos phi minus 2. So this is about Ackermann's. Now in our daily vehicles, please let me know which one we are using. So this is the actual condition, this is the how, let's say without following any Davis and Ackermann's, this is actually the steering gear mechanism that we have seen just before. That was not clear, so let's say this is the actual enlarged view of how it is mentioned over here. This is the front wheel, the front left hand side wheel, right hand side wheel, back wheels over here. W is nothing but the distance between the two pivots. L is taken as to be the wheel base. And whenever it is taking a left turn, see it is mentioned over here, it is taking a left turn. When it is taking a left turn, it is taking, inner wheels are making theta angle and the outer wheels are making phi angle. Just a revision. So here we have seen the condition as, let's say, we have given that, we have taken these two triangles EIO, EAI and EBI, where we have taken cot theta and cot phi. So cot theta is equal to this triangle, this particular triangle I am taking. So if it is tan, that means opposite by adjacent. So it is adjacent by EA by EI. Then cot phi. For cot phi, we have to consider the bigger triangle EBI. For EBI, cot phi is taken as EB by EI. So here EB is again taken as EB is summation of EA plus AB by EI. Then it is EA by EI plus AB by EI. So EA by EI is cot theta is equal to AB is nothing but W by EI is nothing but L. So this is cot phi. So I can take that cot phi minus cot theta is equal to W by L. Next comes single hooks joint. So you can see this diagram. This is how your single hooks joint looks like. There are two C kind of forked elements. They are connected using this cross. This cross is nothing but a plus kind of structure. See, this is it. When you look at from front view and the top view, this is how it looks like. So front view of the driving shaft will look like a circle because you're looking at the circle. This is nothing but stationary. The driven shaft is inclined at certain angle. So whenever the circle is inclined at certain angle, it will not trace an exact circle, but it will trace an ellipse. So the front view looks like an ellipse over here. See, this is the front view and this is the top view. So whenever this AB link is moving with certain angle, A reaches the point A1 and B reaches B1, and the same, let's say simultaneously the driven shaft is also moving with respect to the driving shaft. So C1 reaches, C and D reaches C1 and D1 point. With respect to the driven shaft, the angular displacement is phi here. So C1 to C2, if I produce, it reaches the point C2. Whenever they are traced forward in the top view, they looks like that. So tan theta by tan phi, if I take, it will give EC1 by EC2. See, EC1 by EC2. Because tan theta is taken to be EC by EO and EC2 by EO. When tan theta by tan phi, if I take EO and EO gets cancelled, so they become EC1 by EC2. But EC1 here, if I see, it is projecting the point of OM, right? So EC1 is OM. Now OM is again ON1 cos alpha, okay? Now EC2 is ON. ON is equal to ON1. So here tan theta by tan phi is equal to EC1 is ON1 cos alpha by ON1. So ON and ON1 gets cancelled, they become tan theta is equal to tan phi into cos alpha. So this is the equation from this Hooke's joint. Now we actually want to find the ratio between the angular displacement, angular speeds of the driving shaft and the driven shaft. So how can we find that? We know that the angular displacement angular displacement of the driving shaft is taken to be omega 1 and the angular displacement of the driven shaft is taken to be omega 2. So omega is nothing but the differentiation of the angular displacement, which is d theta by dt, and omega 2 is d phi by dt. So finally when we differentiate this term, tan theta is equal to cos alpha into tan phi, we finally get omega 2 by omega 1 is equal to cos alpha by 1 minus cos square theta into sin square alpha. There are different conditions for equal angles. So when we consider equal angles, equal angular speeds, we can consider it to be omega 1 is equal to omega 2. Whenever we consider that, omega 2 by omega 1 will become 1. So whenever this equation, if I consider this ratio to be 1, I can equate that and finally get the value for tan theta is equal to, this is the condition for equal angular speeds. Whenever the problem is saying, you will get different types of questions, problematic numerical questions based on this. So whenever this equation, this condition is mentioned directly, you can just give this formula tan theta is equal to plus or minus root over cos alpha, and you can find the solution for that. So maximum and minimum speeds are also given for the driven shaft. Maximum and minimum speed conditions, they are given as for maximum speeds omega 2 is omega 1 by cos alpha. This is obtained from this equation only, this particular equation where we say maximum, when driven shaft maximum, then denominator has to be minimum. When it is minimum, we will say theta has to be 90 degrees or 270 degrees if it is minimum. For maximum, this denominator has to be minimum. For omega 2, and this one is inversely proportional. So omega 2, when it is maximum, the denominator has to be minimum. Whenever omega 2 is minimum, this denominator has to be maximum. For such cases, finally we get the equations as omega 2 is equal to omega 1 by cos alpha, omega 2 is equal to omega 1 into cos alpha for minimum speeds. So when these kind of speed variations are plotted on a graph, you get this kind of polar velocity diagrams. So see, this is the elliptical path that you are getting. So minimum position you are getting over here. Minimum is at minimum equal to 90 degrees or 270 degrees, and maximum is at, this is the maximum condition, at 0 degrees or 180 degrees. Okay? And there are also 4 points where they are coinciding, they are having equal angular speed. See, omega 2 is equal to omega 1 over here, this point, this one and this one. So they are coinciding, the curves are passing through the same point. So that those 4 points, 2 angular speeds are going to be same here. Now we also have double Hooke's joint. Here in the single Hooke's joint, what problem we faced was, whenever the speed was given to the driving shaft, the same amount of speed was not observed at the driven shaft. There were different angular speeds. But our motto is to transmit the same power, same kind of speeds. So in order to have that, we have a double Hooke's joint where the intermediate shaft is given so that your driving shaft is having the motion between the driving shaft and the intermediate shaft. This is transmitted over here from the intermediate shaft to the driven shaft. And finally, we get that, let's say that angle turned over here for the driven shaft is theta, driving shaft is phi, and gamma is the angle turned by the intermediate shaft. When there are these three relation of theta, phi and gamma, you will see that tan theta is equal to cos alpha into tan gamma using the equation from the single Hooke's joint. Same thing for the driven and the intermediate. If I want to formulate, it will be tan phi is equal to cos alpha into tan gamma. You will see from the equation 1 and 2 that these two are equal. So tan theta is equal to tan phi, and finally theta is equal to phi. Hence our purpose is solved, that the angular displacement that is given at the driving shaft is same, let's say the same angular displacement is transmitted at the driven shaft also. So double Hooke's joint is let's say having the benefit over a single Hooke's joint. So by this I will end the session. Let us have a quick summary. In this session we have learnt about mechanisms with the lower pairs, different types of exact straight line motion mechanisms, approximate straight line motion mechanisms, also the steering gears, where we have learnt about the condition for the correct steering. Then there are different types of steering mechanisms, saying Davis steering gear mechanism, Ackerman's steering gear mechanisms. We have also learnt about the power transmission, how is it happening from, let's say, one shaft to the other shaft using different Hooke's joint, universal joint, single Hooke's joint and the double Hooke's joint, where we are also into the double Hooke's joint, we are having an intermediate shaft where we are able to transmit the same angular displacement from the driving shaft to the driven shaft. Thank you so much.